Thank you so much for joining us today. So for those of y'all who aren't familiar, I'm Sam Kieber with AC Controls. I'm one of the local account managers here. AC Controls is a rep for Samson control valves, and Samson's one of the top control valve manufacturers in the world. These guys actually developed a lot of the noise calculations that are standards for the industry today. All right, Matt, I'm going to leave it over to you guys.
Okay, good morning. Appreciate everyone taking the time to be with us. My name is Matt Lindo. I am the Eastern United States Sales Director, and I also have joining me David Tam, who's the Manager of Product Engineering. Can everybody see my screen?
Yes, we can see it.
Yes. Okay, perfect. And so just to add to what Sam had said about Samson, we've been in business since 1906, based out of Germany, and our headquarters in the United States is just east of Houston in a town called Baytown. We do everything from R&D to our accounting there, so pretty much cradle to grave. David is part of that engineering team that handles R&D and product management and those sorts of things. And then we have our sales arm there as well. And we manufacture numerous different types of control valves. You'll see some of those throughout the presentation that we'll use for some of the pictures to help you better understand. So today we're going to walk through just a few slides on control valve sizing and selection, just to remind you kind of what CV means and how that's related to a control valve. You may have been on the first seminar. We had a seminar maybe mid last year in 2020, and this is kind of the second step in the series. And then secondly, we will talk about the control valve sizing software. David will give you an overview of how to use Samson software. And then like Sam said, thirdly, we will go into a few different sizing examples that should give you a pretty big range of the different things that you're going to run into when you're using the program and the different things to think about when it comes to sizing and selecting control valves. So if you can see from this picture here, there are numerous different styles and types of control valves. Everything from that small little microflow valve, that third from the bottom left, all the way to a cryogenic valve there in the middle that's used in air separation on a cold box. So how in the world, if Samson makes all these different valves, and this just scratches the surface of the valves that we engineer and manufacture, and then all the other vendors, how in the world do you know which valve to select? Well, of course, there's a lot of factors that come into the selection. And one of those most very important factors is sizing the control valve. And so how do you know which valve to size and select when it comes to economics? Maybe you want to find the most appropriate valve that meets your budget, or like should be the goal of any vendor you work with and of your team, you're trying to find the valve that is the least expensive, that still does what you want it to do. Or how do you select the valve that has the right controllability? The valve that's going to have the control range that meets all of your process conditions and is working in its optimal location to make sure that it continues to control appropriately depending on what the application is. Or thirdly, how do you find the valve that gives you the best performance? Maybe you have some reliability, you don't have a shutdown for 4 years and it's a critical application and it has to last that long. Well, again, one of the important factors in sizing and selection, not the only factor by any means, but is sizing the control valve. And that's what we're going to go over today, is to help you better understand control valve sizing and then to give you a tool that you can use to make sure and size the appropriate valve. So when you look at control valve sizing and selection, these are some of the main criteria when sizing a control valve. You see with the liquid there, upstream pressure, downstream pressure, flow rate, specific gravity, temperature, vapor pressure, critical pressure. So essentially flow rate, pressures on both sides of the valve, directly upstream and directly downstream, temperature, and then your fluid, whatever fluid is going through the valve. And when you look at a gas, it's very similar in the criteria needed to size the control valve, but you do add a compressibility factor. And a lot of this information, this may be small on your screen, is typically organized in some fashion. Maybe you have your own internal document, or as you can see from this document, this is based off of an ISA form. And we've put our Samson logo on there. We can provide this to you. Sam can provide this if needed. You put this information in some type of format, so then you can size the appropriate valve. And essentially what you're doing there at the top section, you can see those process conditions that we just looked at on the previous slide. You're essentially bracketing all of your conditions to make sure and find the control valve that meets those. So you have condition 1, your minimum condition, condition 2, or your nominal or normal condition, and then condition 3, your maximum condition. And what David is going to walk through when he looks at our sizing, that's exactly what he's going to do. So if you look at the basic flow equation for control valve sizing, you see flow rate is equivalent to the CV, that's the valve flow coefficient, times the square root of pressure drop over the fluid's specific gravity. And this is the basic flow equation. There are a number of other factors in this equation. Factors like the liquid recovery factor, some type of piping geometry or swaging factors. There's a number of factors, and luckily for us and for you, you don't have to do this by hand. There are programs, like we're going to show you this morning, that take all of these factors into account in order to select the appropriate CV. And so you see, if we rearrange this equation, now you have the control valve coefficient, CV, equivalent to flow rate times the square root of specific gravity over pressure drop. So in dealing with water and other fluids that are very similar to water, essentially the most basic equation is CV equals flow rate divided by pressure drop. And so what is CV, the valve coefficient? What is it that we're going to show you in the program that we're trying to calculate in order to select the appropriate valve? Well, 1 CV, it's a unitless number. CV is equivalent to 1 gallon per minute of water at 60 degrees Fahrenheit with a 1 pound drop. So if you remember back to the ISA sheet and the process conditions we showed, and now when you look at the CV calculation, the pressure drop across the valve in combination with the flow rate at a certain temperature, that's how you're going to calculate how much CV you need. And I don't know the knowledge level of everyone on this call, but essentially, kind of in layman's terms, the appropriate way to think about it is just think of it as kind of an area or a volume, the amount of space required to flow a certain amount of flow with a given pressure drop. And you can think of pressure drop as a force, essentially pushing that flow through the valve. And so looking at the equation, CV equals flow rate over pressure drop, if your flow rate goes up, you're obviously going to need more CV, more volume or area, a larger restriction or a larger orifice to pass that flow rate. Or if your pressure drop goes up, you would need a smaller orifice. You don't need as big of an area to pass that same amount of flow through the restriction. And what's nice about control valves is that it provides a variable restriction. And so you put an actuator and positioner on this kind of dumb mechanical device, the valve, and all of a sudden you can work in conjunction with your measurement devices that are reading the process variable, whether it be flow or pressure or temperature. Those measurement devices can work with your control system and the algorithms, and they can tell the valve to move to a new location. And so when we're sizing a control valve, you're trying to find a valve that can move to these locations efficiently in order to handle this wide range of process conditions that you would like the single valve to handle. So just one more slide before I turn it over to David to get into the program. I just wanted to touch on, because when he goes through the examples, he's going to show a few different valve styles. And if you remember back to that slide with the numerous different types of valves, you can essentially break these types of valves into three categories. Butterfly valves, that's that picture on the far right, ball valves, and globe valves. A lot of times in an application, well, I wouldn't say a lot of times, but there are times in an application when multiple different valve styles could technically meet the needs of the application, especially from a sizing perspective. You may plug one condition that's your normal operating condition, and that CV that you calculate, you go to our brochures or you use our sizing program and you see that all three of these valve styles have a rated CV that meets that CV. And again, that's why there's so many other factors that come into play with ultimately then choosing the best valve for your given situation. This chart that's shown, I wish I labeled the y-axis and x-axis. I would have got an F in some of my classes for not doing so, but on the y-axis is essentially cost. Think of that as cost. And on the x-axis is CV, or capacity, that we've already talked about. A butterfly valve labeled in the blue line, it's going to give you the most CV for the cost. And so when you think about butterfly valves, there's a lot of benefits and then there's a lot of disadvantages. Some of the benefits are that it's small and takes up a small amount of space. The face-to-face is the least of these three valve styles. It gives you the most CV for cost. So especially when you get into larger valves, a butterfly valve can be very economical as long as you have the right process where the sizing on the butterfly valve is appropriate. But some of the drawbacks is that butterfly valves are not flexible in any regard. It's very uncommon. There are certain valve manufacturers, us included, that have special discs that you can put into the valve to kind of give you different characteristics or handle higher pressure drops. But you essentially get the valve that you get, and it's capable of what it's capable of. There's not a lot of flexibility as you move into what's called a severe service application. And we'll talk about that a little bit more. And so that butterfly valve has a very narrow range in terms of its overall CV capability. It has a narrow range of where it's going to give optimal and ideal control. We typically try to size a butterfly valve between maybe 30 or 40 degrees open, only up to about 60 to 70 degrees open. That's going to be the optimal range where the gain inside of the butterfly valve is appropriate and you're not going to have any chatter. So if it's a fairly static application, you're just trying to hold a pressure and you size the control valve and you see that your typical operating condition is right in that sweet spot for the butterfly valve, then certainly it may be a great choice. And then as you move to the left to the ball valve, you see that the cost per CV is a little bit higher for the ball valve. The benefit of the ball valve, if you've seen them, if you've ever seen a cross section of a ball valve, a lot of them in the control valve world will have a V-notch, and then they'll open up and kind of the ball can get out of the way. But that provides a fairly high rangeability, which is good for applications. It also is a smaller face-to-face and a little bit more compact depending on your piping geometry than a globe valve. But there's also limitations with a ball valve. It's also not quite as flexible as we're going to talk about in a little bit with a globe valve. There are some different options that you can put in for the trim, but it's essentially just whatever you've selected, that's going to be what stays in line. And then you move to the left to the globe valve. And this is commonly what people think of when they think of kind of the Cadillac of a control valve, a sliding stem globe valve. The globe valve gives you the smallest CV of any of the valves if you were to look at the same line size, but the globe valve gives you the most flexibility. For example, for one of our offerings, like that valve that's shown there, which is a Samson 3522, that valve, even in its standard construction for a 1-inch valve, let's say, there are 8 to 10 different trims that you can put inside of that valve in order to hone in on the specific application and make sure that valve is running in its optimal location. And what that does is, economically speaking, it allows you to choose the smallest and most appropriate valve. It makes sure the valve's controlling in its range that it can actually, whatever the application is, it can respond to those signal changes. And then thirdly, it provides the best reliability. It ensures that the valve's not oversized and working near the seat or something in that regard. And so these are the 3 different types of valve styles, and you're going to see these in David's example that he's going to walk through later. Okay, now I'm going to turn it over to David Tam, and he's going to open up our software program and share his screen and walk through that with you.
Thanks, Matt. All right, let's go ahead and get this opened up here. So hopefully this is, like you can all see my screen now. Yeah, I appreciate the short introduction. That's a lot of what we consider a lot of things to consider when trying to select a control valve for your particular application. What we're going to show you here right now is the program, the tool that we use to do a lot of this and make an appropriate selection. As Matt mentioned, there's various different types of control valves, and a lot of times there will be some overlap on what's appropriate. So we'll look at a couple of examples as well and see how each of those kind of apply and where we can try to select the best possible valve. So as you can see here, this is the sizing program itself. I've got open on the display. Hopefully some of you have this program already. If you do not and you would like access to this program, get in touch with Sam and we can send you a link to download the sizing software. It's just a basic install program for the computer. I'll kind of go over some of the functions here and just a couple of minutes talk about some of the features of the program that'll make it a little bit easier and a little bit more fluid to work with. So if you know a couple of the tips and tricks that you can use to make it work best to your advantage. So if you can see here, like any general program, we've got our basic command bar here on the top. I've already opened a new project. When you open the sizing program, what I would always recommend is working in a project instead of an individual file. So if you click new, you'll just open up a single individual valve tag. But the way the program functions, it's a lot easier to work as a project, even if you're only doing one valve. So I've got it opened here where you click create new project, or you can open a project that you've already started. So that's the main basic functions here. We have preferences, of course, several different languages that it's available in, your unit preferences, and a couple of different additional options that you can work with as well. And then some of these I'll have to get started to show you a little bit more of the functionality here later on. So we'll go ahead and open up a file, open up a sizing for an individual valve. So if I click on this down arrow here, you can see it gives me a list of options, and we'll click a standard ANSI valve to start off with. So when I do that, you can see it opens up the first position here within the project. A couple of things that we're looking at, kind of some basic commands here. You can see, opening a file, things like that, more or less basic commands, save and print, and we'll look at those in a few minutes. In the basic header information, as you see here, you can enter, an item number, and we'll call this a flow control valve as our tag, just as an example. Here you can select the media that you'd like to use. You can either select it from the drop down here, or you can type in something manually. If it's available in the drop down, then all of the media information will be in the database that we have here. So for water, steam, and air, always stay at the top as the most common 3 media that you'll see. And then beyond that, there's a pretty extensive list. So we have a lot of these, a lot of different media here. If you scroll to the bottom, you can also hit search. This will take you to the medium database. And once you get in here, you can see there's a substantial number of different media where we have all of the media information. And as you can see here, some basic, all of the basic medium data based on the pressure and temperature that you have. So that's a list there that if you want to look through, you'll have a lot of different information, and that saves you some time from looking things up in a table somewhere. You can also select the state. For most of the known media, it'll automatically select the state based on the operating conditions that you provide. But if it's a manually entered medium, then you can also tell it what state the medium's in. And then here we'll see the valve type and the actuator type, and we'll look at that briefly once we get into the sizing. So the next area here is where you would enter your process data. And then the final tab is where the medium data will be entered. And again, for anything that's in the database, that will come in automatically, or you can enter it manually if you have a special media or you have slightly different conditions. If it's a mix of media, something like that, that's where you can enter your data manually. So the best way, I guess, to look at the rest of the functionality is to go ahead and jump into one of the first examples I have prepared, just to see how we would work with the program, and then show you a little bit about how you would select a control valve based on the results that you find. So if we open up the process tab, you just click on the process tab here. The way most of the program works, all of this information you can edit by double clicking, and then it'll open up a general input area. So when we look at the process data here, we'll double click and it opens up this window, this dialog window. I'll go ahead and start entering a case. So we say, just as an example, let's say 100 gallons per minute. We still have water selected as our media. We have 100 psi at the inlet, and let's say 95 psi at the outlet, and just ambient temperature conditions. This will, as you're cycling through, you can use the enter button to cycle between. If you hit enter again, it'll take you to the medium data. As you can see, it's automatically populated based on the water data for the given conditions that we have. So we can cycle through. One kind of helpful functionality here is if you click on one of the numbers, you click and hold it, you can drag it to the next position, and that'll allow you to copy over your data. So if we're going to do a similar case, let's say for case number 2, we want to look at the same pressure conditions, but we have half the flow rate. So we'll look at maybe 50 gallons per minute with the same pressure and temperature. Then that'll allow us to leave all the other conditions the same. allow us to save a little time there. Now, if you use tab to cycle through each of the cases, then it will skip and it'll stay within the window you're in. So that's one of the functionalities of the program, that using tab versus enter to change from case to case. And we can do the same thing here. We can drag across, and we'll keep, let's say we keep the flow rate the same this time, and we'll change the downstream pressure to maybe 80 psi, something like that. So now if I hit enter again, you can see the program's automatically populated all of our medium data. So we can select OK, and then we have all of our process information that we need. As Matt mentioned briefly, the important things being the flow rate that we have here, the inlet pressure of the valve. So this is what's being supplied. This is coming upstream where at the valve inlet. And then P2 is going to be your pressure at the outlet of the valve side. So those are both critical for determining the CV value of the valve, what flow capacity we need in the valve to be able to handle these particular conditions. And then we have our temperature as well. So that allows us to determine the rest of the media information and pull this. So Matt introduced a specific gravity in the program. It's entered as density, but essentially the same thing. And then we have our vapor pressure of our media. That's going to tell us a lot about, give us warnings about cavitation and things like that, which I'll introduce as we go to a little bit more advanced calculation. But for the first one, we'll look at this here. It'll be pretty straightforward. The critical pressure of the media, and then the viscosity of the media as well. So you have all of your process information that's going to influence the valve. So once we have all that entered, pretty straightforward. We have two different buttons here. So we have one that looks like kind of a valve symbol, and that's how you calculate the valve. And then afterwards, we'll look at this here, which would be to calculate the actuator that we need for that particular valve. But the first thing we want to do is determine what valve we need to handle the process conditions we're looking at it. Then we'll look at the actuator we need to be able to actuate that valve. So I'll go ahead and hit this here. And you can see it'll populate several different results. We'll go through that really quickly here at the bottom. As you can see here, one of the most important results of the valve itself is going to be the CV value. This is going to be the amount of, as Matt described it, the area, the amount that you need to allow the flow to pass through. The area may actually be different in different styles of valves, so it's not a direct correlation to the area that the flow passes through, but in a simplistic view, it can certainly be considered kind of that way to get a picture of what the purpose of that is. So for each of these conditions, this is going to tell you we need a valve that has a minimum of 44.7 for a CV value. If it's 100% open, it will pass exactly that flow. So the second case, as you can see here, when we have half the flow rate, we're going to have half the CV value. So 22.3 instead of 44.7. And then if we look at here, we have our, if we increase the differential pressure on the valves, so cases 2 and cases 3, we've kept the flow rate constant, and now we've just increased the differential pressure. And as you can see, that's also dropped the CV value. So because we have that larger differential pressure, we don't need as much or CV to be able to pass that same given flow rate. So that's the first result you're going to see from the sizing. The next result is going to be a required size. So we use a couple of different factors to determine a minimum recommended size for the valve. And one of the crucial parts of valve sizing is also to consider the outlet velocity of the valve. And what's important here is after you're throttling the media as you go through, and particularly with a globe valve, and you'll see these limitations will change depending on the size and style, things like that. But the outlet velocity will tell you, because you have a certain volume in the outer half of the valve, You don't want to have too extreme of a velocity where other media could be creating jets and could potentially cause erosion over time to the material itself. So that's one of the things that we certainly take into consideration when we're trying to determine the appropriate valve size for a particular application. So that will be the recommendation here. We'll also receive the flow velocity as a tabulated value here. So you can see here the different flow velocities, and then the sound pressure level that we have as well. So the sound pressure level is the approximated amount of noise or sound that's going to be audible at 3 feet distance away from the control valve itself. And there's various standardized equations that we have for calculating those. I'll look briefly at a couple of factors, then I can come back to that once we look at the factors themselves. So as you can see, after I click the calculate valve button, it's automatically selected a valve for our particular application. So you can see here, in this case, it defaults to all the minimum requirements. So it will default to a 3-inch valve. As you can see, we need 2.86 calculated minimum size. So it'll go to the next available nominal pipe size here. In this case, it would be a nominal pipe size of 3. And then it will select the base minimum pressure class. This is a class 125 cast iron. So it would say that in this particular case, that would be appropriate. I know I would say 99% of applications, we would typically go to a carbon steel, so a class 150, and we can make those modifications in just a moment. But based on all of these selections, it selected a valve with a CV of 70. So that's going into the catalog and finding the next available CV value to give us the best travel for that particular valve. So if we look here, we can see our relative travel is then given as 75.8 in the maximum case, down to 38.5 in the minimum case. So this is a fairly good control range for this application, so we can leave the CV value as it is. A couple other values that it's going to provide, and this is what we look at, again, going into a little bit more detail once we get to the critical applications, is you can see the XF value. This is a differential pressure ratio. So you can see as we have a very small differential pressure in case 1 and 2, that's going to be a very low number. In case 3, we're increasing the differential pressure ratio. So that will give us a slightly higher number. And so this is a ratio compared to the vapor pressure to tell us how close we are to cavitating. One thing I'll mention here, if you click on the help, and then if you click on contents, that's going to bring a lot of these different different information and explain it as well in more detail. So for the sake of time today, just because we're a little bit limited, I'm going to breeze over a few of these topics that we could certainly go into a ton of depth on. And so you can read in here a little bit more. So you have your FL, XT values, a lot of these different values that we're looking at, and it'll explain more detail how you calculate these numbers, what's the importance of all these values, things like that. And certainly, if you have more interest on the topic, we can schedule some more time to go through that in more detail at a later time. But just for the sake of time, we'll kind of go through these quickly. So we have our FL value, which is the recovery in the valve. We have the XFMR, as you can see, is related to XF. This is going to show you when the valve should experience critical cavitation. So as long as this value, the original XF, is lower than the XFMR, then we should be in good shape. And then the FD value, then we have, that's where we would see, start to see the beginning of choking cavitation. And some of these may be a little bit different than variables that you're used to from other manufacturers. So this is just nomenclature that Samson has been using in developing our software over many years. The XFZ value, this is an incipient cavitation. So again, goes back to the same FX value, XF value. This will be incipient cavitation. Then we have F1 and F2. These numbers are tabulated values that are plugged into the sound pressure level calculation. So these are values that you're going to see used in order to calculate the sound pressure level. And so F1 and F2 are important. If you're sizing a gas, it would be G1 and G2. They'd be slightly different factors, but those are going to be the important factors for the size for the noise calculation. So that brings us back to what we're looking at here, and that's why I also wanted to introduce that first, so we can talk a little bit about one of the other functions that the sizing program has. So if we look at this, the calculation standard, as you can see here, we're calculating it with the Samson standard. So what that is it takes the IEC equations, the standardized, up-to-date equations for predicting sound pressure level, but within the actual standard, it just has generic values for for the F1 and F2 values here. So what we've done is we've gone through for all of our main valve series. We've measured these in the laboratory and calculated measured and tabulated all of these values so we can input more accurate values for sound pressure level. So it gets us a little bit more accurate. However, if you'd like to do it just according to the IEC equations, so that would be this final one here. It's IEC and it's also an EN, a globally harmonized standard. So you can change that here and then calculate just purely based on the standard instead of using the tabulated values that we have. Finally, we can get into the valve selection itself. So if we double click in this area, as you do with the rest of the program, that'll bring up a dialog box here to change things out. First thing, typically, even though the class 125 would typically be available here, we can change it to a 150, and then we can change to carbon steel, would be a lot more common to see. For sure, so we've got those changed. Everything else, we can typically let the program select this from the database, but you can also use this program to calculate generally any type of valve, even from other manufacturers. So if you want to use the program for that as well, you certainly can. And here you can type in tabulated values from whatever valve you're looking at. So you could type in a particular CV value. It gives you a drop down of the available CV values in our valves, but then of course you can manually enter it. For calculating the actuator, these will all be important to know that the travel of the valve, the seat bore. So that's going to tell you how large the trim is so that you know how much force is going to be applied from the flow. The flow direction of the valve will always default as a flow to open to get the maximum or best possible controllability within the valve. And then we have some noise reduction options we can look at later as well. Here we can go to the next dialog box. I hit enter here, or you can click this tab and then double click to open it. These are more some secondary options that if you want to tinker around with this, if you get a larger valve and you need pressure balancing, you can use that here. If you need leakage class 5 or leakage class 6 for better shutoff, you can select that here. And then also specifying if you have a bellows section, for example, for hazardous media, or an insulating section for higher temperatures. And then finally defining whatever your internal materials you'd like to be. You can do that all here. Piping information, as you can see, everything's going to be populated by default, but then if you have, let's say, a 3-inch valve with a 4-inch pipeline, you can enter that in here. And that's one of those factors that Matt mentioned at the beginning for the influence of the CV value. There is a correction factor. If the valve size is different than the pipe size, that will slightly influence the CV requirement. So if you change that here, you can see the influence and then select the valve appropriately. It'll also influence the noise calculation as well. And then finally, we have the actuator results, which we can go ahead and do that. If you look at the program, you can see now it's grayed everything out. That mean when it does that, that means that we've changed something in our selection. So once we go through and we start making modifications, and this will need to be recalculated. So it's not going to recalculate every time you change something, just to prevent the program from lagging, but especially when you're making multiple changes. But you can go through here and just hit the button again. And we'll get a couple of dialogues here. Sometimes it'll recommend a different stroke length or something like that. We say, do we want to use what we've already got in there? You can say yes, or if you want the program to select it automatically from the database, you can say no. So we'll do that with a couple of things, and then the stem diameter. So a couple of things changed when we go from the cast iron version of the valve to the carbon steel version, which is a more heavy duty, rugged design. A couple of those factors are going to be a little bit different. So it'll give us a prompt to let us know it's changing those values. So we've got our base value, we've got our base calculation done here. We've got all of our factors and results. The sound pressure level looks good. We can see our relative travel looks good. Everything's fine. Now we can go into our actuator selection. So we go here, and the most straightforward way, you can just hit the calculate actuator, and that's going to populate the results. It will automatically go into the database and select an appropriate actuator. In this case, it's our type 3277 with a 350 diaphragm. Looking at the results briefly here on the left, you can see the very first result is going to be the most important. The force required here is going to be 584 pounds. So that's what we're going to need to shut off against the media that we have. The second factor is more of an internal factor, so I wouldn't pay too much attention to that. This third is a maximum allowable. So based on your selection, based on the stem diameter, based on if you have a soft seat, for example, for tight shutoff, it will tell you what the maximum allowable force is from the actuator for that valve. So this is what you don't want to exceed, or you might start to cause damage to the valve. So we'll need our actuator to be between at least 584 to get shut off, but then under 6,300 pounds to exceed what's possible. You'll see the DP max here, and then this will take your diaphragm area of 350 and it will say if we have this diaphragm area, you need a spring range starting at exactly this value to achieve this force. Now, if we look at the actuator results here on the right, it automatically will it'll find the maximum of all three cases, and it will input that as your P1. You can go back and manually increase that if you want to say, you want to have, for example, maybe 125 PSI shutoff. So we can do that here. It'll say that this is different than this, but you can say yes, let's retain the user entered values. And now we can see we have a new force required of 705. Same actuator, still suitable, so not a problem. But you can see now we need at least 14 PSI. So when we go back to our actuator results here in our selections, by default, it's going to fail close. That means the stem is going to extend down into the valve to close the valve. This is going to be the nominal size of the actuator itself. The bench range is going to be how the actuator is operating. So there's a specific number of springs inside of the actuator. And when you apply your supply air from the positioner to the actuator, the amount of air that's being applied to the bottom to compress those springs is what these values are. So we add 20 psi of air to the bottom of the actuator, and that's when the actuator is going to just start moving. So that's when the plug is going to start lifting off of the seat. And as we continue to apply pressure into the actuator, we'll reach 34 psi, and that's when the valve's going to be 100% open. So when we say this is our operating range, it means between those two values of pressure and the air side of the actuator is where we're going to see operation. So what's going to give us our shutoff, the important part for us here, is going to be the 20 psi at the bottom side. So we applied 20 psi from the springs, assuming there's no air inside the actuator at the time. So force times area, or pressure times area, gives you a force. And that's where we're going to get our actuator force here. You can see in this this cell is going to be 1,085 pounds of force, and our minimum required is 705. So the next value underneath, and this is really the critical one to look at, is going to be your safety factor. So this is the force required divided, the force required divided by, or the force produced divided by the force required. And so this is going to be 1.54. So as long as you're over 1.1 is what we set as an absolute minimum, just to be safe. But then for most, we'll try and size it about 1.25, just to give yourself an extra bit of reserve for the safety factor there, and make sure you're shutting off. And then you can input your supply pressure here, and this is important if you're failing open specifically, because then the springs are pushing upwards, and the amount of air pressure you have to close the valve is going to tell you the difference between the upper range and the supply is going to be the most important. For fail close applications, you just want to make sure that the supply air is a couple psi higher than the upper part of the bench range, to make sure that you can push that actuator all the way open. And so if you input a smaller supply here, it'll recommend a different spring range that's suitable, that fits within that lower supply. Let's say if you only have 30 psi of air supply, for example. So that covers kind of the most basic case, I would say here, just kind of a general overview of what the program's doing. Once you get all of your results, we can look at here a sizing, for example, and we can print out our sizing. We can include the main calculation sheet. We can also include the diagrams. Let me show you a little bit about that real quick now that we have some results. So if we click here at the top, this button here is our diagram button. It'll show you a couple of different things. You can see for this, it's got our valve type 3241 selected, and it's going to show you the percent travel based on a measured curve for our particular valve. If you're sizing another valve from another manufacturer within the program, it will put in this case, it's an equal percent curve, and it will just use a generic equal percent or an optimal equal percent curve. But since we have tabulated values for the stroke at every percent for our valves, it'll input that particular curve and then show you where each of your operating cases are going to be on the valve curve. As you can see here, the CV value, we have a nominal CV of 70, so that's our yellow line, and that's where we're going to be at 100%. In this case, it's actually just over 100% based on the measured value. So it's a nominal value of 70, but we, depending on if that trim set is being used in a 3-inch valve or a 4-inch valve, it might vary slightly. So this is a particular tabulated value where it reaches the nominal value. So you can see we achieved just over 70. So actually at 100%, it'll just be at about 66 actually for this particular combination of that nominal size. And then we'll see here, we also have a pressure temperature diagram, so you can see for each of the pressure classes it'll take for a particular material. And what you can do to zoom in here, if you click and you just drag a box, it'll zoom in on what we're looking at. So you see yellow line is class 600, green line is class 300, the red line is class 150. It'll put an X at our design conditions, and then it'll give us a triangle. That'll actually show us what our maximum allowable is for a particular temperature that we're operating at. That'll give us our maximum value. As you'll see here, it's converted, it's in bars and Celsius. That's just based off the ASME standards. So it uses what's tabulated in ASME to pull that out and enters that and shows you there on this graph. So those are going to be the main general functions of the program, and looking at a very simple application. Now we can look at another application here. I'll create a new sizing. So a couple of different functionalities that you can do with the program. When you click this down arrow again, if you just click the plus, it's going to do the same thing we did last time. So it'll go and it'll create a new ANSI standard. You can also copy this position. You can copy the first position or the last position. So if you're making duplicates and you want to, or let's say you have a selection that you really like, then you can copy that, and or you know, you don't want to mess with, let's say, but you can copy it and then tinker around with the CV value and then delete it and go back to your original if you like. So that's a good way to see your additional options. I'll go ahead and just create a new sizing and call this number 2. And we'll look at this case. This would be another case where, like Matt mentioned, maybe the controllability and having a very precise control valve like a globe valve is not the #1 priority, and we have a very small differential pressure, which means we need a larger CV value. We can look at another operating case. Let's see here. So let's say 400 gallons per minute, and then we'll use 100 psi, and then we'll just do a 1 psi drop. So something very small that's controlling flow, but you're trying to minimize pressure drop, something along those lines. So you can see here, we'll just enter the first case just to do a sizing. On the header, we can go and if we calculate, or we'll calculate it as a globe valve to start with. Our medium data, again, with water is automatically populated. We hit a sizing. As you can see here, if we keep it as a globe valve, we'll need an 8-inch valve, and that's because the CV gets very high. The maximum CV of a 6-inch is right around 400, and it has a minimum 1.1 safety factor on the CV value as well to make sure you're not exceeding the stroke of the valve. So this will actually bump us up to an 8-inch valve to achieve the flow that we need. Then we can consider potentially using another style of valve. So as we talked about, possibly a ball valve might be a good option here. You have full ball valves more as isolation valves, and then for control we would look at a segmented ball valve. So that is basically just a ball segment, and it's used more for control. That minimizes, or I wouldn't say minimizes, but it reduces the amount of friction when you're operating compared to a regular ball valve. And so that helps to control better than you would out of a standard ball valve, plus has general better flow characteristics to improve control. So for a control valve here, we have a segmented ball valve, and we can change that and then recalculate. And as you can see here, that changes our valve completely. So now we can use a 4-inch valve. As you can see, this is our type 3310 for a segmented ball valve. And we'll look at it. We have a CV of 700 here, whereas a globe valve would have a CV of only around 400 for the same application. So this is a good example to show you where we can change the style of the valve and reduce the valve size. So if you noticed on the valve calculation, also the required size is a little bit smaller here. The CV is much higher, but that's available for this particular flow condition that we have. One of the other challenges that we'll run into, and I'll show you guys a slide here real quick to describe a little bit more what we're talking about next. And this is just one quick thing to mention, cavitation within a control valve. So when you hear the term cavitation and you hear the term flashing, this is where those terms come from. So we have our P1 and our P2. So we have our the black line would represent what's happening inside of the control valve. As you can imagine, this black line is very exaggerated just to show our show what's actually happening, to help it accelerate, to help illustrate what's happening. But essentially the principles are the same here. So we have our inlet P1, and then we have P2, which is going to be a lower downstream pressure. So we're dropping pressure inside of the globe valve. Well, as we flow through the vena contracta, so the throttling area inside of the control valve, we're going to have a minimum pressure. And this is because the cross-sectional area is much smaller than the downstream side of the valve. So you're going to have a lower pressure here, and that's where you're doing your control. That's where you're dropping your pressure, and then it will recover downstream. So this vena contracta pressure is critical, and this is illustrated with the pressure recovery factor that we looked at earlier. And so that will have an influence on if cavitation is taking place and how much. Now, from the operating condition side, you can see those are the colored lines here that we have. And these are going to illustrate the vapor pressure of the media. So P1 and P2 are what's operating, and then the vapor pressure is going to be based on the media itself. So if we have a vapor pressure between 1 and 2, then we're going to be flashing. So this is going to be where we're dropping, we have liquid at the inlet, and then the vapor pressure is higher than the outlet pressure. So your media is going to be transitioning from a liquid to a vapor. The beige, as we look here, is going to be cavitation. And then the green, this is what, like we looked at in the first case, where the vapor pressure is very low in comparison to P1 and P2. So we're not in any danger of having that vena contracta pressure drop below the vapor pressure. So there's no cavitation, nothing to worry about. So here is what we talk about, and this is one of the most critical services for control valves, is cavitation and how much of it is actually taking place. So when you look at P1 and P2, the vapor pressure is lower than both of those, so it doesn't look critical, but in fact, while you're throttling, your pressure will briefly drop below that. So as you drop below, you're going to start to form vapor. Vapor bubbles within the flow, and then it recovers downstream, and those vapor bubbles implode and create microjets, and that's what can cause damage to the valve trim. If you're not careful about valve velocity, you can see here as some of those high velocity jet streams could carry those cavitation bubbles and implosions onto the valve walls themselves as well. So that's where you need to, that's why it's important to look at the velocity as well. And so that's just a brief introduction into what cavitation is inside a control valve. So now that we understand that, I'll plug in an example here and show you some of the warnings that you'll get from the program once we see that. So I'll create another example here, and we'll call this one a pressure control valve. And again, we'll use water as an example, and we'll go a little bit higher pressure on this one to see the effects that we have here. So again, we'll do 100 gallons per minute just as an example, and then 500 PSI at the inlet, and we'll do 200 PSI at the outlet. So we have about a 300 PSI pressure drop, and then we have 70 degrees Fahrenheit. I'll do a second case here, so I'll drag and drop, and this one I'll drop our downstream pressure to 0 PSI. So we're going all the way from 500 PSI down to ambient. Another function I didn't mention at the beginning, but if you want to work with differential pressure, so you can click here the drop down to change units, and it'll give you quite a few different options for units. You can click delta here, and that'll be P1 and then your differential pressure instead. So you can see 300 PSI, and this will do a full 500 PSI pressure drop. But I'll put this back into P1 and P2. So we have our conditions here, and I'll hit size again. So now you can see we get a couple of warnings as we calculate these. First is going to be cavitation noise. So that's when we're dropping from 500 down to 200 PSI, and we have cavitation noise. This is creating some noise. So we would recommend, looking at potentially using harder surfaces, something like a stellite surface trim, to prevent a little bit of cavitation taking place, but mostly it's just generating a little bit of noise, and it's not causing a lot of damage. The second case here is much different, and you can see here it says critical cavitation. So you get this warning here that that cavitation that's taking place is going to be critical to the control valve. So what we'll look at here, another thing, we can see the relative travel might be a bit high for our liking, so we can go to a CV of 12. We'll use a class 300 carbon steel. And then I'll go ahead and just recalculate this again. Oh. We'll say yes, we want to keep that CV value. So now we have our calculation here. How we notice that, how we recognize that something's taking place here, you can see the XF value is now much higher. So this is almost a 60% pressure drop in relation to the vapor pressure, actually a 58%, and then now this one is 97%. So that XFMR that we looked at, which we said was really important for what we call critical cavitation, you could say this isn't yet within our critical cavitation zone. It's getting close, but it's still just cavitation noise, whereas this one is above the threshold, and therefore we deem this critical cavitation, and we want to look into some anti-cavitation designs. That again, we'll probably have to get into a separate training to look at more of the specific various different types of anti-cavitation trim that we have, but just as a kind of a basics, as an overview, this will give you that warning to say we need to look into using some special trim to be able to handle the critical cavitation that we're seeing here. Again, our sound pressure level will be much more elevated. We have a sound pressure level of 78 and 79 in this case. So a little bit more critical than we would see in a standard valve. Another thing to look at is if we'll take this first case out again, just to remove the critical cavitation. And we'll recalculate. So another thing to consider when we talk about the type of valve, like we mentioned, this is a globe style control valve. We selected in the header here. And here we say it's cavitation noise. It's not necessarily critical. So with cavitation noise, we can add some stellited surfaces, but we don't need to worry about the longevity of the valve too much for this one. This will definitely last with some hardened trim for a significant amount of time, and will work very reliably. However, if we have these same operating conditions and we want to consider another style of valve, as Matt mentioned, like a butterfly valve, we can size these same conditions in a butterfly valve. And now you can see the sound pressure level is much more elevated, and we do get the warning that we have critical cavitation here. So this is another case where we would see, you can see the XFMR, the critical cavitation threshold, is much lower for a butterfly valve. So it would start to become critical cavitation much more quickly. So while a butterfly valve would be good for very small differential pressures and achieve a very high CV value and provide a very economic solution, a low profile solution, it would certainly be it would certainly have challenges handling these particular differential pressures. So we want to use that type of valve for those applications. The same thing if we look at a ball valve, we can try that out here, and you see the same thing with over 300 psi differential pressure. That ball valve really would not be the ideal candidate to handle these particular applications. One of the other things that you'll notice as well, if we have a CV of 60 or 160, and the operating, because we have a very high differential pressure, we have a very small CV requirement. So we'll see that here, that the relative travel is fairly small on that one, but the CV is much larger on a segmented ball valve than it is on a globe valve. And the globe valve also has various different trims that you can put in to optimize, as we saw at the beginning there, and select appropriately to achieve a good travel. So if we go back to a globe valve, we can calculate here to populate our results. You can see it usually just uses a safety factor of 1.1. a few of the other functionalities of the program here at the bottom. If you double click on this 1.1, you can change that to, let's say, 1.3, and that will automatically then give us a little bit higher CV value. So if you want to get into a more, you want to leave a little bit more buffer between the CV value and the required CV value, that will that you can do here. Typically, we use 1.1 just so it doesn't oversize the valve too terribly much. But of course, there's no, exact program that you can add that'll be perfect for every single application. So, we could look at that safety factor, and I usually bump that up to 1.2 or 1.3, and that'll get us in a very good relative travel range to where we are, to what we need here. So that's a few of the basics from my side, just talking very generally about the program, some of the functionality of the program, some of the things to look out for when you're sizing. One last thing I can introduce here would be just for saving the program, for example, or saving the sizing. So you click Save As, it's all pretty straightforward. So I can save this on the desktop, and you can reopen your program accordingly. Other than that, it's pretty straightforward, like a standard program would be. So there's nothing too critical here. One thing that we can look at is the printout. So I'll go ahead and do a print preview. So we can see this is the standard printout that we have, and then we can do a couple of different formats with the printout, but this would be the standard printout view. And you can see here, this will give us all of our process information that we entered. It'll give us the basic results that we were all looking at there. And then in the final sections, it will show us the valve data that we've selected here. I'll go back to the first one since we did a complete valve. We have our buttons here. This will switch between valves, and then this will go all the way from the beginning to the end. The negative or minus button here will delete a sizing that exists. I'll go ahead and do the print preview here because it's been fully completed. And you can see here all of our results, our valve selections here, materials, leakage class, bonnet selection, piping that was used, and then it'll also give us our actuator data, our operating conditions, our supply, and then all of our actuator results down here that we looked at: required force, the max force, and then ultimately our closing safety factor that we have here, which is critical. So that basically wraps it up from what I have prepared. I'll invite Matt and Sam to join back in the discussion. We can go over a few of the questions that we have here. Let me go back through.
Perfect. Yeah. Why don't you, David? Why don't you leave that open, and we'll walk through the questions, and a few of them you may need that program. Yep. I'll go ahead and walk through them. I wrote them down here so we didn't have to scroll through that list. So the first question was regarding noise attenuation options for ball and butterfly valves. As we talked about, globe valves have, the most options when it comes to severe service and handling cavitation. But when you look at ball and butterfly, most control valve manufacturers will have some type of option on their ball valves and butterfly valves. For example, David touched on our VTEC valve, a rotary plug valve. We have various, whether it's on the ball for a ball valve manufacturer or like us, we've got various downstream options that are kind of part of the seat on the outlet of the valve. And so they're essentially drilled holes so they can stage the pressure drop to make sure that your pressure does not fall below the vapor pressure and cavitation doesn't happen. Or from a noise perspective, they will shift the frequency so it's outside of the audible range and lowers the noise that a human can hear. And also on butterfly valves, we have special looking discs that do the same. Let me just show you quickly here's a picture of on our rotary plug valve, those options. And then also here's on a butterfly valve. This is our Loish triple offset valve. You see these attenuation plates that we can put onto the disc. All right. So hopefully that answers that. And now the next question. Are fuels in the sizing database? So David, you showed some of the medium in there, but
Right, there are some in there. I don't know if there's a particular fuel in mind. I know there's a whole lot of them. So yeah, there's some of them I have seen are missing. So there's not it's not literally every media you could dream of, but it's a pretty substantial list. So there are several fuels that are in there. But it would really be if there's a particular fuel that we're looking at, and it'll get down into the, there's quite a few different things. So it'd be really, yeah, looking into a lot of the just different options that are available as a particular media. But by and large, I mean, there's several thousand media built into the medium database.
okay. All right, perfect. Thirdly, they were asking about the close-off pressure for the actuator, and that was before you eventually did address that.
Okay.
As he showed, considering the shut-off pressure in your application, we will select an actuator. The program will select an actuator that's appropriate for the shut-off pressure. If you remember, it will grab your P1, your upstream pressure, and put it into the database, but then you can modify that if your shutoff pressure is higher than that. So hopefully that answers that question. Then the fourth question is the flow velocity being calculated at the vena contracta? Loved seeing that. You know, somebody's interested in control valves when they ask that question. So if you remember, David talked about, and we probably all remember back from our days in college, Bernoulli's equation. So as you're moving through that restriction, trying to pass that same amount of flow, you're going to have an increase in velocity, and there's going to be a decrease in pressure. And so that is calculated. That's the highest velocity point. But I think, David, they were specifically asking when you were discussing outlet velocity.
Correct.
And so is that what is taken into account when we put that into the program?
Exactly. So it's the outlet velocity as well, and that's actually what's displayed is going to be the outlet velocity once the media has exited the vena contracta and essentially has entered that larger volume on the downstream side of the valve. So vena contracta velocity certainly is important as well, and that's taken into consideration in the sizing, but what's displayed here is going to be the outlet velocity. That's also a critical velocity for us when we talk about once the media has left the vena contracta and reaches that larger volume, and so that's what we really look at as critical for the downstream side. So.
Okay, perfect. Question number 5, what happens if the calculated CV range is too large for a single valve to span? So before talking about the program, of course, the initial answer is you may need to move to 2 different valves for the application, but always remember to look at other valve styles. Maybe you're originally thinking that a globe valve can handle it, or you have a globe valve installed and you think I'd like the same fit, form, and function, the same face-to-face, so I don't have to do piping mods. Well, remember that you could move to a valve with a higher range ability to maybe handle it. But considering the program, what type of warnings will it show, David, if the valve we've selected doesn't handle those 3 conditions?
So sure, exactly. We'll get a warning here, so we can say, let's say 0.5 gallons per minute. So something, or even something smaller, maybe 0.1 gallons per minute. So we have generally that would be a 1,000 to 1 turn down ratio, which would generally be impossible for any control valve to worry about. So we'll keep all of our selections the same here. Let me do that again. And as you can see here, in the following cases, the capacity is smaller than the rangeability. So you'll get a pop-up warning, and then it'll show you case 3 here. If we close it, additionally, when you're looking at the results, you can see the CV value is much, much smaller. If we go to the relative travel, it'll just give you this little indicator that it's basically 0. So once you achieve, once you get to a very small CV like that, that's the warning that you'll get.
Yep, and I'll just add to that. I mentioned it on the one slide considering butterfly valves in terms of the best control range. Well, for a ball valve, that increases a bit, and we typically like to stay between 20 and 80 degrees open. And then for a globe valve, we'll typically like to see 10 to 90% open. So the program, even if it doesn't give you a warning and the valve technically can move to that location, when you go look at the curve on the results, you can see that it might be outside of this control range. And that's when the interaction with us comes in handy to understand that. And maybe you tell us, well, my minimum case is only going to be, in some situation for 20 minutes a day as I just fine tune the amount of steam I'm sending into a vessel or something. And so even though it's at 7% open, we can have that discussion and say, well, that's not going to affect the reliability, and it can still be handled with the rangeability of this valve. Okay, so then the last question I see is, does Samson have fuel service valves for fueling solutions? I'm not sure all the details with this question. David, do you want to address it?
Same, I would say, in a general sense, certainly we do. If we're talking about, a particular application within a fueling station, that would be, come really down to what exactly the application is. We certainly do a broad range of both pneumatically operated and control valves, and then also we have quite a few self-operated regulators that will basically use the medium pressure themselves to operate independently. And a lot of times you'll see that in these remote locations and areas where you want a fixed constant outlet or inlet or something like that. You'll use a self-operated regulator for those. So we have various different options for those particular applications, but would have to look at it, based on exactly what we're looking at there.
Yep, very good. Okay, I think that addresses all the questions. We are so thankful that you've joined us. Sam, if you want to say some closing words.
Yeah, sure. So I looked over here in the chat section. I do have a list of names for those wanting to get the PH credit. So I'll send out an email with the form for you guys. If there's anyone else who's interested in that, just let me know. And other than that, if you have questions on getting the software or whatnot, please feel free to leave your information here too, and we'll get that over to you. Thanks, guys.